Complex numbers are a combination of a real number with an imaginary number. A real number can be defined as being all the numbers we already know, such as 3, 1054, square root of 7, minus 0.5, 1.25, etc. I think that these examples give you a good idea of what a real number is. However, an imaginary number is something a little more complicated. The definition of an imaginary number is that when it is squared, it will give a negative result. So far, we have never really come across any of these numbers because it isn't something that usually occurs. This is because when we square a positive number, we get a positive answer, and when we square a negative value, since we multiply by itself, the result will also be positive. To be able to understand the imaginary numbers, we have to be able to imagine that such numbers exist. The unit for this number is I, and it equals to the square root of minus 1. This corresponds to the definition, since if we squared this number, it would actually give us a negative result, minus 1. Some examples of imaginary numbers are 3i, 1054i, square root of 7i, minus 0.5i, 1.25i, etc. The I in those numbers is to simply remind us that we have to multiply by the square root of minus 1. A complex number is defined as a plus bi, for which a is a real number and bi represents the imaginary number. Both of them can be 0, so technically all the real numbers and imaginary numbers are complex numbers. Julia said and Mandelbrot said are both really easy to generate with computers, which makes it that they are both famous sources of fractal images. For both of these sets, it is the same equation that will be used. However, we will be exploring different variables of the function with each set. The function used is z squared plus c. In Julia's set, the parameter z will be evaluated. To do so, a constant c will be chosen and be used for every possible value of z. Then we have to use the iteration process to know how quickly the point will head for infinity, or if it stays bounded. In this process, we have to take the possible value for z, square it, and then add the chosen constant. After obtaining a result, we square it and add the same constant and keep repeating this until the result shoots to infinity or converges. One aspect that makes things more interesting is that the complex numbers are used for the parameter z and c. However, for the Mandelbrot set, it is the parameter c that is explored. To do so, we set the value of z to 0 and replace c with any possible value. By doing so, we obtain a set which is represented by an image. The image can actually let us see a lot of points that are trapped by the formula. Just like in the Julia set, the points outside the image formed with the equation escape to infinity, and the ones inside are the ones that stay bounded. The determination of the color of the points outside the image are based on how fast the result shoots to infinity. For example, if the value shoots to infinity at a slow rate, it will be colored orange, red, yellow, etc. And if the value diverges at a very quick rate compared to the other values, it is usually colored blue. The link between the two sets is that for every point in Mandelbrot's set, there is a Julia set that can be created.
The fractal that we pick is this. The software gave us this Mandelbrot's figure. However, after choosing two complex points, one in the black area of the fractal and one in the colorful area, calculating many iterations for each of them, and graphing the complex points, we realized that both points diverged. Confused, we tried other complex points in the supposedly converging area, and all of them were diverging. Later on, we discovered that the software could not develop equations, and therefore ZOS does not give us the real graph of our Mandelbrot's figure. When we put the developed version of our equation in ZOS, this is the figure that we obtained. As you can see, there is no black area, so all the points in this figure diverge. For the purpose of this project, we will continue using Mandelbrot's figure obtained using this equation. As you can see on the figure, there is a black area which is supposed to represent the converging points of the set. The colored points closer to the black area, yellow and red, take longer to diverge to infinity than the blue points. The complex point that we expected to converge taken inside the Mandelbrot set is C1. This is a Julia's equation for this point and its fractal. The second complex point taken outside the Mandelbrot set expected to diverge C2. This is the Julia's equation for this point and its fractal. Both complex points are strictly increasing, therefore they are monotonic. According to the calculations and the graphs, both points diverge almost at the same rate on the graph. We can see that for the first three iterations, the rate at which it is diverging is relatively slow. As we can see for iteration 4 and 5, the values start to shoot off to infinity at a quicker rate. In conclusion, the Mandelbrot set that we picked was not a good choice because the software used was not able to analyze our function properly to give us an accurate image. This led us to believe that our fractal had both convergent and divergent points. However, we came to the realization with the help of the teacher that our fractal was a plain circle with no converging values. In conclusion, the Mandelbrot set that we picked was not a good choice because the software used was not able to analyze our function properly to give us an accurate image. This led us to believe that our fractal had both convergent and divergent points. However, we came to the realization with the help of the teacher that our fractal was a plane circle with no converging values.